Hi there. In this next series of lectures, we're going to see some of the basic security concepts as applicable to not just distributed systems, but also as used in general computer systems. So there are many different kinds of security threats that can be launched on a distributed system or any system that uses servers. Three of the common security threats are leakage, tampering, and vandalism. Leakage essentially means that someone gets unauthorized access to a service or to a data, that they're able to read the data or access the service while they should not actually be able to. For instance, if someone else gets to know your bank balance, who is not authorized to know your bank balance, who is not one of the account holders on your bank account, then that's leakage. Tampering goes a step further, where someone not just gets access but is able to modify data or is able to modify the service. For instance, if an unauthorized individual modifies the balance in your bank account without you having authorized that, without you having written a check or done a bank transfer, then that is known as tampering. And finally, vandalism essentially means that someone interferes with the normal service or normal operation of the system without necessarily benefiting directly from this attack. The most common type of vandalism attack is denial of service, where, for instance, a particular service may be inaccessible to legal customers because an attacker is bombarding that service with a lot of unnecessary messages. So these threats are typically carried out via some attacks. Some of the common attacks are listed on this slide. Eavesdropping essentially means that the attacker is able to listen to messages by tapping into the network. For instance, if someone is able to intercept all the messages in the network, then they're eavesdropping. Masquerading goes a step further, where the attacker is not just able to read messages but is able to pretend to be someone else. And you'll see an example of this as we discuss some of our security protocols. Essentially, this is similar to identity theft, but in the computer world, where a machine claims to be acting on behalf of user Alice, while in fact they're acting on behalf of user Eve, who is evil. Then you have message tampering, where the attacker is able to modify messages in the underlying network and send them forward so that they can, for instance, masquerade to be someone else. You have replay attacks, where the attacker is able to replay old messages. This is a particularly insidious form of attack, where by replaying old messages, for instance, you can prove yourself to be someone else that you're not. And finally, denial of service is typically carried out by bombarding a particular port, say the HTTP port, so that the other regular messages by valid legal clients cannot get through that port just because of being overwhelmed by the other messages being sent by the attacker. So how do you address these challenges? Well, there are three properties that secure systems typically try to provide. These are known as the CIA properties. They stand for confidentiality, integrity, and availability. Confidentiality essentially says that you're protected against disclosure of your data to unauthorized individuals. This addresses the threat of leakage. It says that your data is essentially confidential and only those who are allowed to read the data are able to do so. Integrity essentially says that only those who are allowed to alter the data are allowed to do so, who are able to write the data are allowed to do so. For instance, for your bank account, it may be only you who is allowed to alter the data, and of course the bank, who might be acting on behalf of you. Anyone else would not be able to alter or corrupt your data. This addresses the threat of tampering. And finally, availability says that the service or the data is always reachable, is always readable and writable. That is, you're able to carry your operations on the service or the data. And this addresses the threat of vandalism. So these three properties are examples of properties that we desire in a system. This is what we want the system to achieve. We haven't yet said how the system achieves these three properties. So this difference between what and how can be laid out by differentiating between policy and mechanism. And this is one of the key aspects, key concepts in distributed systems as far as security is concerned. This is very important for us to understand. This has been advocated by many scientists and is actually used by secure systems today to differentiate between what and how. A security policy indicates what a secure system wishes to accomplish. Okay, so this is typically a human level goal of what you want the system to be secure against and how you want it to be secure. For instance, the CIA properties, the confidentiality, integrity, and availability properties are properties that we desire from a secure system, and so these are security policies. A security mechanism, on the other hand, indicates how these goals are accomplished. So given a security policy, you can design security mechanisms which then implement that particular policy. For instance, you could use encryption capabilities and a variety of other mechanisms that we'll all see in this series of lectures to implement a given set of policies. It's very important for you to be able to distinguish between a security policy and a security mechanism, because typically these are separate, and it's not always the case that a set of security mechanisms always accomplishes a security policy. That gap is typically what a designer of a secure protocol needs to bridge. So what kinds of mechanisms exist? Well, there are three types of mechanisms that are popularly used. These are known as the golden A's by some security researchers. They are authentication, authorization, and auditing. Authentication essentially is a mechanism that verifies that a user claiming to be, say, Alice is in fact Alice. And of course, the user is communicating over the network, so the only way you have of authenticating the user is via message. Suppose we authenticated the user and we know that Alice is in fact Alice, but we need to check that Alice, who is trying to access file foo, in fact is allowed to access file foo. Is Alice really authorized to access file foo in the particular mode that Alice is attempting to? That is what is known as authorization. That's the second A. The third A is auditing, and that stands for essentially knowing how a particular attack was carried out. So for instance, if Eve managed to attack the system and gain access to some data, how was that attack carried out, so that we can fix the system for the future. Typically, this is done by logging all the operations in the system and then later on looking at the logs, mining the logs, perhaps replaying the logs and figuring out what went wrong. So how do you design a secure system? Well, essentially, it's kind of hard to do this because you don't necessarily know how powerful your attacker is. Your attacker may have access to data centers. Your attacker may have the capability to listen to all the messages that are in the underlying network. So when you design a security protocol, first you need to set down on paper what your attacker model is. What are your assumptions about what your attacker is able to do? For instance, you might assume that your attacker is able to read messages in the underlying network, but is not able to modify messages. A different attacker model might involve the attacker also being able to modify the messages. So what are exactly the assumptions that you assume from your attacker? This is very important to lay down on paper. Of course, this attacker model should be tied to reality, which means that you can't just make up an attacker model out of thin air. It needs to actually be an attacker model that is somewhat real, that corresponds to real attackers. So once you have the attacker model, then you have the problem statement, and you now need to design the security mechanisms that satisfy the policy that is specified as a part of the problem statement. Then you need to analyze and prove, perhaps formally prove, that the mechanisms that you have designed in fact satisfy the policy under the attacker model that you have assumed. And this is an important part of any secure system design. Finally, when you design a secure system, you need to analyze the behavior of your system when there are no attacks. This is the common case. Attacks do happen, but they're not the common case. They happen rarely. And when there are no attacks going on, you want your system to be as fast as when the system did not have any of your security mechanisms in place. Okay, so analyzing the effect of your security mechanisms on the overall performance is very important. Typically, when you add security mechanisms to an existing system, which was insecure to begin with, you're going to impact the performance of the system. Perhaps the throughput will go down by a few percentage points. If your throughput goes down by, say, 2 or 3%, then that's probably acceptable performance overhead. But if your throughput goes down by 100%, then you're in trouble, because now you're incurring a much higher cost for the security mechanisms, and that's probably not a good set of security mechanisms anyway. So in the next lecture, we're going to see some of the basic cryptography techniques, very basic cryptography techniques, and then after that we'll use cryptography to implement some of the mechanisms that we have seen in this lecture.